Hi, let's go over our next section, 4.9 Antiderivatives. This is going to be a fun section. Plus, it's also going to prepare us for our next chapter, and for you, this also means for the next class. All right, our goal of differentiation is to find the derivative formula developed in previous chapters to discover corresponding antiderivative formulas. So, what is an antiderivative? For now, our explanation of an antiderivative is undoing a derivative, so the opposite of a derivative. So if we have, for example, the derivative of x is 1, this implies that the antiderivative of f of x being 1 would be f of x being x, because the derivative of your function equals your f. In this case, the uppercase f would be the one before the derivative. All right, an antiderivative, a definition. A function f is an antiderivative of f on the interval I provided that f prime x equals f of x for all x in I. However, you may recall we lose the value of the constant when finding the derivatives, so we must keep that in mind when working with antiderivatives. So, for example, what's the derivative of x plus 1? Isn't the derivative just 1? What about the derivative of x plus 2? Isn't the derivative also just 1 because we lose that constant? So there's a way to keep track of the constant. Next, we have theorem 4.14, a family of antiderivatives. Let f be any antiderivative of f on an interval I, then all antiderivatives of f on I have the form f plus c, where c is the arbitrary constant. So let's make that word part of our vocabulary, the arbitrary constant. In other words, don't forget to add the plus c unless stated otherwise. There will be situations in the future where you will not need to write the plus c, but for now, always write the plus c. So let's talk about antiderivatives. Let's do an example. Use what you know about derivatives to find all the antiderivatives of the following function. All right, so here we have our first example, f of x equals 3x squared. So what we know about derivatives, for example, we know the power rule, right? So let's do some examples. Say I had 2x to the fifth, now I take the derivative. We would go ahead, multiply to the front, and then we subtract 1, right? So what if we want to do the opposite? Well, I would want to add 1 for sure, right? So far we have this x to the third power, but I need this something here. Now I know that when I take the derivative, I want to get here. So I want my answer to be 3. But I know that I should be bringing it forward. So in other words, think 3 times what gives me 3. In this case, our desired number is 1. So that we have just 1x to the third power or just x to the third power. That is our antiderivative. And if you're ever unsure of your antiderivative, you can always check it by taking the derivative. So if I have x cubed, let's take the derivative, let's multiply the 3 forward and subtract 1, so that I have 3x squared. That is exactly what we started off with. Next example, let me change it to an exponent that's negative. So that I have negative 9 raised to the 10 to the negative 10 power, so that I can deal with that denominator differently. Okay, so to undo that subtraction that I do with derivatives, I would want to add a 1. And that is for my antiderivative. So far I have 10 to the negative 10 plus 1, and I want to have something. I want to have a something such that my answer after I multiply would be -9, and I have -10 plus 1, that would be give me a -9. When I take the derivative and multiply -9, my answer should also be -9. So what is this number? We get 1, right? So we have 1 x raised to the -10 plus 1, we get -9, which is just x to -9. And I know that right now it might feel really weird, but I promise you with practice, it will feel second nature. It's going to require a lot less effort as you practice and you do more of these problems. And again, if you want to make sure you're right, you can always take the derivative. So what's the derivative of our answer? I'll bring the 9 forward, so -9, and then I subtract 1. So I have -9x to -10, which is our original problem. That's antiderivatives. Let's do one more. Those trig functions. Those trig functions require a lot more effort, mainly because they require you to kind of partly memorize them or be very familiar or know what to do with them. So we know that the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine. So how can we find the opposite of the derivative? Let's undo the derivative. So you want to think, what derivative gives you sine? Well, the answer to that is cosine, but we need that negative that's missing. So negative cosine. Our answer would be negative cosine. So you're working backwards. That is an antiderivative. And again, if you're unsure, if you're kind of stumped at the moment, you can always double check your work. So let's take the derivative of our answer. So negative cosine of x, take the derivative. The derivative of cosine is negative sine. So I have negative sine, which gives me positive sine of x. And the first negative is from here, and then we bring out the other negative. That's where the double negative came from. And we see that's exactly what we started off with. Except that somehow in between I changed from t to x, but it was always supposed to be a t. Sorry about that. All right, indefinite integrals. So here are some pieces of indefinite integrals. Indefinite integrals, we use that little s notation. And the integral of f of x dx means to find the antiderivative. So this is our antiderivative notation. The function is called an integrand. So our f of x, that's called your integrand. Dx means in terms of x, or the variable of integration. The integral of f of x dx, this notation presents all the antiderivatives of x. So don't forget the constant of integration, that plus c. All right, so in case what we did with the integrals was confusing, make sure you practice using this formula. Theorem 4.15, power rule for indefinite integrals. So this is kind of a formula that's helpful so that you can go ahead and take those antiderivatives, find those antiderivatives. So this says that we have a function x with an exponent p. To find your antiderivative, you're going to take your p and add 1, and then divide it by the exponent p plus 1, and don't forget your plus c. And this works as long as where p is not a negative, because when you add, you're going to get 0 for an exponent. Theorem 4.16, constant multiple and sum rules. The first one is the constant multiple, and that just says if I have some constant, some number, in my integrand, I can go ahead and just move it on the outside, and it will not affect my answer. The second is if I have two terms, as an integrand, I can go ahead and split my integral. And sometimes that helps us see the question a bit more easily without focusing on this long integrand. All right, so let's take a look at our first example. let's go ahead and integrate. Let's find the indefinite integral. All right, so according to my sum part of my rule, I can go ahead and split this so that I have my integral of 3x to the 5th dx plus my integral for 2 minus 5, my integral for 5, square root of x. And if I forget a dx, I'm sorry. All right, now let's go ahead. According to my constant rule, I can go ahead and move my constant forward. So that 3, well, that 2 is part of my integrand, but that 5, 3 and 5 I can work out. So that I have 5 with my, oh, I write 5, 3, and then my integral of x to the 5th dx plus my integral for 2 dx minus, I can bring out that 5, my integral, and instead of writing square root of x, I'm going to write x to the 1/2, just so that's easier to look at. All right, now from here to integrate each, you can go ahead and use your new helpful formula to evaluate integrals, which we have right here, right? If you have some exponent, you're going to go ahead and add the 1 in the numerator, in the exponent's place as well as the denominator. So I'll do that first one with you. So I have x, 5 plus 1, and the bottom I have 5 plus 1. The antiderivative of a constant is just that number with a variable. And then here I have x, 1/2 plus 1, so plus 2 over 2. The bottom I have 1/2 plus 2 over 2. All right, don't forget about your constants. Okay, now it's just a matter of cleaning it up. So I have 3 times x to the 6 divided by 6 plus 2x minus 5 times x to the 3 over 2 divided by 3 over 2. Let's clean up a bit more. So we have 3 over 6 x to the 6 plus 2x minus, and think about it here, 3 over 2. When we are dividing, what do we do with that second fraction? We change it to multiplication and we flip it, right? So it'd be the same thing as multiplying by, instead of 3 over 2, it'd be 2 over 3. So that we have 2 over 3 times 5 over 1. All right, let's finish cleaning it up. My fraction of 3 over 6 is now 1/2 x to the 6 plus 2x minus 10 over 3x to the 2 over 3. Not so bad, right? It just takes a couple of steps. Next example. Now for this one, let's go ahead and rely on our algebra rules. Or we can also make that a statement. Okay, so remember, what does the bottom exponent do to the top exponent if they have that same base? They subtract, right? So in order to have this, denominator, we can use our algebra rule so that we can have 4x and 19 minus 2 is 17 minus 5x, negative 8 minus 2, negative 10. And that's something that we can more easily look at, right, to try to integrate. All right, let's go ahead and try to integrate. Now, if you'd like to, you can use your separation of terms, or you can just go ahead and do it in one shot. Let's go ahead and split it. So we have 4x to 17 dx minus 5 x to negative 10, and we're going to integrate that. Okay, so according to our integration rules, we're going to add 1, 17 plus 1, and then bottom I have 17 plus 1. Don't forget that 4. On the other one, we're going to add 1. So I have negative 10 plus 1 is 9, negative 9. Negative 10 plus 9 is negative 9. And don't forget about that 5. And something I forgot the last one. Don't forget about your arbitrary constant. All right, now it's just a matter of cleaning it up. So we have 4x to the 16th over 16. Did I subtract instead of add? I did. 18, not 16. Minus negative 5 over 9, x to negative 9, plus c. Here we can work with that minus minus. And let's reduce this fraction so that we have 2 over 9x to the 18 plus 5 over 9x to negative 9 plus c. And that is our antiderivative. Let's do one more. Now, when you have two products, the way to go about it is to FOIL the integrand or expand. So if we do so, we have 2z cubed minus 5z squared plus 2z minus 5 dz. Then you go ahead and take the integral. I'll let you try this one. Your answer should be 1/2 z to the 4th minus 5 over 3z cubed plus z squared minus 5z plus c. All right, now let's talk about trig functions. We can also take the integral or the antiderivative of trig functions. It's just a matter of being comfortable with these derivatives of trig functions. So you want to think, what derivative gives me? In this first problem, we have secant square root of x. We know our value there is tangent. So to undo that and do the antiderivative, our answer would be tangent of x plus c. So it'll be more complex, as we will see in the next couple of examples. But to help you out, just as we had a chart that gave you all these derivatives, we also have a helpful chart to give us all of these antiderivatives or integrals. So this is a table from your text, table 4.9, indefinite integrals of trigonometric functions. And here you can see it tells you what the derivative is, and therefore it tells you what the integral is. So here's where it splits between your integral and your derivative. So you can see it's just a matter of looking at which way you're reading your problem. Okay, let's do another example. Now, the sum rule for integrals is very helpful when you're working with trig functions because I see how it might cloud your understanding if we have a number there. So we can easily take this first integral, right? But here, that 3 is, at least for me, at first sight, it kind of looks odd. So why don't I move that 3, that constant, to the outside of my integral so that I have 3 integral cosine of x. Okay, that helps. Here, my integral would be just an x squared. And then here, we're left with 3. The integral of cosine is sine. So our answer is x squared plus 3 sine of x. Next example. Okay, so you have your handout with you. Does sine x divided by cosine squared, is that any of my integrals? It's not, right? So I'm kind of stumped. I don't know what we should do. Whenever you feel that way with trig functions, go ahead and use your trig identities. That's very helpful. So let's go ahead and write this. This is the same as sine of x divided by cosine of x times cosine of x because it's squared. I know sine of x divided by cosine of x, that's tangent x. So I have tangent of x times cosine of x. Is that something, an integral that I can work with? We see that, well, not quite. I have my tangent, but it seems like if I had a secant, I can work my way to secant. And we see that cosine, well, I made a mistake. This is 1 over cosine. So we have tangent of x times 1 over cosine. Let's rewrite it as secant x. Now that's something I can work with. So I can go ahead and take the integral of tangent of x times secant of x. And we see that that's one of my integrals. The integral of secant of x times tangent of x is secant of x plus c. So we have secant of x plus c as our answer. All right, and I'll let you try this one on your own. My suggestion here is to go ahead and move your constants out of your integral. All right, next we have Introduction to Differential Equations. This is a fun class when you take it in the future. Differential equations is one that people usually enjoy, or so I'm told. All right, so an equation involving an unknown function and its derivative is called a differential equation. Here we will work to find the value of the constant when finding the antiderivative. I'll do one example with you because your idea is almost the same. So the following problems solve the following initial value problems. In other words, find C. Okay, well, let's think about what we have. This f of 1 equals 1/3. This tells us that I have the point. This tells me that we have the point 1 comma 1/3 given. This is part of a point on the function. On your function f of x. But we don't have f of x, we have f prime, we have the derivative. So what we're going to do next is, or better yet, since we have the derivative, let's use the antiderivative to find your original function, f of x, then plug in x and y from your point x comma y to find your c. All right, let's go ahead and label our steps. So first we're going to find the antiderivative. So that we have f of x equals, okay, so the antiderivative of x squared, well, that's going to give us an x cubed. We divide by 3 minus the antiderivative of negative 2x is an x squared. And don't forget your plus c. Okay, next on our plan is we're going to plug in that value. Our x is going to be 1 and my y is going to be 1/3. And I get that from this point right here. Okay, if we plug that in, we get 1/3 equals 1/3 to the third power minus 1 squared plus c. That leaves our unknown only being c. All right, let's do some work. So I have 1/3 equals 1/3 minus 1. You subtract 1/3 of both sides. We move the 1 over. You get c equals 1. So that our function f is actually f of x equals x cubed over 3 minus x squared plus 1. That's our actual function. You see that constant was lost when we took the derivative, but now we went through the trouble of finding it. All right, that's it for this section. I hope you enjoyed it. Thank you.